so we're very convinced that dark matter must exist. But we have yet to say what it is. The ideas of what dark matter could be tend to fall into two categories. The first one is that it is made up of ordinary matter, the stuff that we already know and understand. It's what makes up the Earth and the Sun and all that stuff. But it is very, very compact and is not giving off very much light. So it has very, very high mass, but isn't giving off very much light, so we can't see it. Now, these things have to be predominantly out towards the halo in our spiral galaxies to help explain the rotation curve. So these things are known as massive, compact, halo objects, or machos. Some examples of what machos could be: we have brown dwarfs. So remember, a brown dwarf are these objects that are close to having as much mass as a star, but they didn't quite get enough to begin to get the pressure and temperature in the core to begin fusion. Okay, so they're high mass, but they don't have fusion, so they're very dark. Cold white dwarfs, neutron stars, and black holes. All of these things are macho candidates. All right, here's our second lecture quiz question. What is gravitational lensing? A, bending of light due to gravity. B, reddening due to gravity. C, the change of gravity due to the curve of space. Go ahead and think about it, and we'll discuss in just a bit. It is A, bending of light due to gravity. Okay, so it is A. So the whole idea of machos is that we can't actually see them. But even though we can't see them, that doesn't mean that we can't figure out that they exist. The whole idea is that we're going to have to use the influence of them to figure out how many they are. Specifically, what we can do is we can look out towards the halo at stars that are way out there. And if a macho passes between us and the star, then the star's light will focus onto the Earth due to gravitational lensing. So out here's the distant star, and here's us, and here's the macho coming through. Before the macho comes through, we only get the light directly pointing at us. But as the macho crosses through, some of the other light will actually get bent so it focuses onto the Earth. What this means is that the distant star will suddenly become brighter as the macho is coming through, focusing that light, and then it will fade back out once the macho is crossed through. Okay, and it's going to follow a very specific light curve. So we can look all through the halo, doing these large sky surveys, waiting for one of these chance encounters. But knowing how often they happen can actually give us information on how many machos are out there. Well, when we do these studies, and it's been done a couple of times, when we take the most optimistic view, meaning that we skew the statistics in the most positive way that we can, then machos make up between 10 to 20% of the dark matter. In other words, it's not machos. It's absolutely not machos. So the other possibility for what dark matter is that it is made up of weakly interacting massive particles, or WIMPs. So we know it's not the machos, it has to be the WIMPs. The WIMPs win in this case. So the idea of a WIMP is that it is a subatomic particle. So think things like electrons and protons and neutrons. However, it's of a type that is not common, that we don't actually know about. And they have unusually high mass for being such tiny little particles. Now, if you take your favorite extension to the standard model of particle physics, we have candidates for what dark matter could be. Okay, they could be axions or sterile neutrinos, okay, or all of these other sorts of weird, bizarre particles that may be predicted from the math. However, when we go out and we actually build experiments to try and find these things, we can't. And this has been going on for a long time, at least since the 1980s. Okay, we have built experiments searching for dark matter of particular types, predicted by the possibilities of what's in physics, and they don't exist. We cannot find them. So we're certain that dark matter exists, and it pretty much has to be WIMPs, but we still have no idea exactly what it is. This is our current understanding. It's a little bit frustrating. Now, although we don't know exactly what dark matter is, that doesn't mean that we don't know any of its properties. So we can actually look at astronomical events to tell us something about dark matter. For example, in this image, what we're looking at is the bullet cluster of galaxies. Now, this is actually two clusters. There's a cluster here on the left and a cluster over here on the right. What's particularly interesting about this is that these two clusters have recently passed through each other. Now, in this image, the yellow blobs you see, those are all galaxies. So we know exactly where all of the galaxies of each cluster are. The red regions here in the middle, this is the hot X-ray emitting gas. If you remember back when we were talking about clusters of galaxies, rich clusters are often embedded in this overall X-ray emitting cloud. That's what this pinkish reddish stuff here in the middle. Then the blue regions are where the dark matter has to be located based off of gravitational lensing. So we know where the galaxies are, we know where the X-ray emitting gas is, and we know where the dark matter is. So what is interesting is comparing all three of those. So notice that the galaxies have pretty well continued on their merry way. Yes, there is probably some gravitational disturbance, but if they pass through fast enough, there's not going to be very much. Then, notice what's happened to the X-ray gas. The X-ray gas has actually been stripped out from these galaxies. As the two clouds have pushed on each other, the clouds of gas, due to pressure, have slowed down. So the galaxies kept moving, but the gas has slowed down, which is why it's kind of trailing behind either cluster. But notice that the dark matter didn't get slowed down. The dark matter moved on through just like the galaxies did. What this tells us is that the dark matter does not interact electromagnetically. The pressure that the X-ray clouds felt actually comes from the electrons in the atoms pushing against each other. Because the dark matter regions did not slow down, that means that they didn't feel this electromagnetic repulsion, this pushing of the charges together. Okay, so this means that dark matter does not interact electromagnetically. This also helps us understand why it is that we don't see dark matter. If you remember previously when we talked about light, we said that light was an electromagnetic wave, meaning that it exists because of the properties of electricity and magnetism. Well, if dark matter does not interact electromagnetically, then it will not interact with light. Specifically, it will not give off light, meaning it's not luminous, but it will also not absorb any of that light. The light passes right on through without being affected. So we say it is dark matter, but I think that a better term would actually be invisible matter, because it does not interact with light in any way. Now, last time we started talking about the large-scale structure of the universe. This is how matter is distributed on the biggest scales. So we talked about filaments. These are these chains and walls where galaxies are located. And then in between, we have these pockets of nothing, referred to as voids. Well, this large-scale structure actually shows the influence of dark matter. So shortly after the Big Bang, the universe had a very smooth density, meaning that stuff was distributed pretty much evenly all throughout everywhere, except there were very, very slight density disturbances. Okay? Places that had slightly higher density and places that had slightly lower density. Well, the regions that had higher density had greater gravity, so was able to pull more and more stuff together, and this is where our filaments are eventually going to form. Places of lower density are going to have material swept out away from them, and these are going to form into the voids. They don't have enough stuff to form galaxies. Well, we've actually been able to create computer simulations of how it is that this large-scale structure formed. And in these models, you can manipulate all sorts of different properties. You can say there is dark matter or isn't dark matter, and what kind of dark matter, meaning is it WIMPs or machos, and even tweak some of the properties of the WIMPs. Okay, well, the only computer simulations that lead to a large-scale structure, to the scale of filaments and voids that we actually see in the universe, the only computer simulations that work are the ones that have dark matter as WIMPs in the amounts that we've talked about. So even how galaxies are distributed through the universe shows that dark matter must exist, and that it has to be WIMPs. Now, do we know exactly what it is? No, but we do know that it must exist, and we're starting to get ideas of some of its properties.